So hello everyone and hope you all are doing good. So this is a follow-up video regarding my book. So what will I be covering in this particular? So first of all, thank you all for the overwhelming response to my first video. So I have so many messages pouring in my WhatsApp that I have to make this particular video to address all your queries regarding this book. And another important thing that I'll be doing in this particular video is discussing a chapter from my book so that you get a better idea as to what actually is there within the book and how it will help you for the exams. And I'll also be releasing a sample paper from my book for all of you to attempt so that you can assess for yourself as to where you stand now. So starting with the important questions first. So the first important question that I came across was, does this book cover everything related to radiophysics and no other material is required? The answer to this is no. The book has all the possible questions and concepts that you will come across while preparing for your FRCR, MD and DNB exams. So it's like a question bank along with important concepts. However, the basic understanding of the chapter requires reading of standard texts like Far's and Sara Abdullah's notes. So I'm not replacing them by my book. One. The main problem that is faced by all the students studying for this exam is basically application of that particular knowledge or concept, and that is what I am teaching in my book. Standard books are like ocean of information. Even I have read from it and developed my concepts, but the problem is that from that ocean what you have to take in and how to apply it in the questions that are coming is the main important thing that you have to understand and figure out, which I'll be helping you in. The second question is, when should I get the book? That is, in which year of residency? This is another frequent question that I've been asked. So the thing is, whenever you want to learn to apply those concepts in solving questions, you should get the book. So that is as early as possible. Third, what is the price of each copy and what does it include? So the price of each copy is 2,650 to 2,700, which includes postal charges to your location. And depending on your location or delivery, these are the charges that have been prepared. Along with this, I'll be giving you access to my WhatsApp group, which is dedicated to radiophysics, where I'll be sharing all my videos which I've made on radiophysics and also some text material for the exams. So this cost has been decided after a lot of deliberation, and individual sources from which I have prepared this book after compilation will cost you much more than this. So let's now discuss a particular concept of radiophysics with the help of a standard book as well as my notes. So first we'll be reading standard text like Sara Abdullah notes, and then we'll be seeing how my notes will help you with this particular concept. So let me start with fluoroscopy. So fluoroscopy is the use of real-time X-ray imaging with the help of image intensifiers. So what exactly is an image intensifier and why is it required in fluoroscopy? So if you give a long exposure time, so this is real-time imaging like barium meal, barium follow through, all these things require a long exposure time. So if you expose the patient for a long period of time with a large radiation dose, the dose will be very high. Hence, we use very small currents like 1 to 5 milliampere current we'll use throughout the exposure time. So in that case, the resolution is compromised. So to actually intensify that resolution or brightness, we use image intensifier. So that with a low radiation dose, we can actually get a better image quality. So the image intensifier TV system is characterized by the ability to convert the input light into a much higher output or gain or intensification. The X-ray input image intensifier tube is a vacuum glass or ceramic envelope surrounded by a metal housing to shield it from external sources, light sources and magnetic fields. Now if you just read this statement, you will just read and you'll just go on with it. But the thing is, there are 2-3 MCQs that are formed even in this particular paragraph. So that is why the application is very important. For example, the X-ray image intensifier tube is of vacuum glass. It doesn't have any inert gas or any gas within it. Second, it is of metal housing to shield it from external light source as well as magnetic fields is what is important. They will give true and false questions giving external light source but no magnetic field, and you'll think that it is not MRI, why need shielding from magnetic field? But the thing is, it shields from both external light source and magnetic field. The degree to which an image is intensified or amplified is given by brightness gain, which is the ratio of brightness of the output screen compared to the input. Again, one MCQ has been formed because output screen to input screen. They will ask whether it is a brightness gain from input screen divided by output screen. So that is wrong, false. Then brightness gain is actually a product of minification gain and flux gain. So in turn, minification gain describes, because the input phosphor is much larger than the output phosphor, there is a gain called minification gain, and flux gain is because the electrons are accelerated from the input to the output phosphor, and because of that potential difference there is a flux gain. So the product of this is called brightness gain. So minification gain is diameter of the input screen divided by output screen whole square. Another important thing is, because the flux gain cannot be measured that well, which is not very well described here, we use this conversion factor, that is image intensifier conversion factor, which is luminescence of the image intensifier output divided by image intensifier entrance dose rate. So the factors that affect brightness gain of the image intensifier tube are magnification and flux. So minification gain is in the order of 100, flux gain is in the order of hundreds, and the conversion factor is in the order of 10s to 30s. This is very important. So now coming to the basic structure of an image intensifier system. So where exactly is the image intensifier placed in this system? So image intensifier is formed of input screen, electron optics, and output stage, basic construction of the image intensifier. So image intensifier is actually above the patient. That is, X-ray tube is beneath the patient. The X-rays pass through the patient and then they hit the input screen of the image intensifier first. So image intensifier, the input screen consists of input window, input phosphor, and photocathode. Everything of this particular input screen has a particular function. For example, image intensifier input window is a convex metal shield that covers the input face and is made up of aluminum or titanium foil of low atomic number, and it allows the X-ray beam to enter with minimum attenuation, and it provides protection for sensitive input components of the tube and maintains the vacuum. The input phosphor, this is very important. It is made up of sodium activated cesium iodide. It has been asked multiple times. It has good X-ray absorption efficiency, that is about 70 to 90%. And it has tiny needle-like crystals with fiber optic-like characteristics. And it is 400 to 500 micrometer thick. And each X-ray photon produces about 3000 light photons in the blue spectrum. Then coming to the photocathode, the fluorescent emission from the phosphor then is absorbed into the light activated photocathode, which is comprised of antimony cesium, thin layer of antimony cesium alloy that has spectral sensitivity well matched with the blue light emission of cesium iodide, sodium activated cesium iodide. And the absorption of the fluorescent light photons releases a pattern of electrons from the photocathode of the image intensifier tube, and approximately 200 electrons are released per X-ray photon that is absorbed. So each X-ray photon produces 3000 light photons and approximately 200 electrons are released per X-ray photon that is absorbed. Now coming to the image intensifier electron optics, that is, the input screen is maintained at a negative voltage with respect to the anode with a potential difference of 25 kilovoltage. This means the electrons produced are accelerated across the image intensifier tube and carefully focused on to the output screen, which is 1/10 the diameter of the input screen. That is why the minification gain. So the electron focusing is done by the focusing electrodes, which are metal rings within the tube that are held at positive voltages, fixed positive voltages with respect to the photocathode. This constrains the electron in the tube to travel along a path. So they focus it into the output screen, and such that the intensities in the input screen are actually replicated into the output screen. How does magnification occur within an image intensifier? Unlike an X-ray, magnification and image intensifier is actually electronically achieved by actually this focal point where the electrons cross over before reaching the output screen. It is brought closer to the input screen for magnification. Magnification causes the image to become less bright, so the brightness gain decreases, dose to the patient increases, but the resolution improves. So these also have been asked multiple times. So the output screen is formed of silver activated zinc cadmium sulfide crystals which are deposited on the inner surface of the output window that convert the electrons into light photons again. And the output image is intensified significantly by the acceleration of the electrons and the minification of the image that occurs in the image intensifier tube, and the screen is normally 25 to 35 millimeters in diameter with few micrometers thick. The inner surface of the output screen is coated with a thin layer of aluminium which forms a part of the anode structure. This is also very important. They will ask whether the output screen is only formed of zinc cadmium sulfide. So no, it is also formed of aluminium. And what is the job of aluminium? Aluminium, actually the layer is opaque, preventing the light emitted by the phosphor from backscattering. So it prevents backscatter basically. So then there is an output window that is optically transparent glass block port through which the intensified light image exits the image intensified. And this is a summary of the entire chapter. So now you should be able to solve the questions regarding this particular concept. So starting with my first question on fluoroscopy. So concerning an image intensifier, the glass envelope contains inert argon gas. This is the first statement. Whether it is true or false, you have to tell. The metal housing is designed to prevent stray light getting into the tube and to shield from the magnetic fields. This is the second question. The focusing electrodes are designed to channel photons from the input screen directly towards the output screen. True or false? The input screen is much larger than the output screen. The input phosphor is one large flat crystal. I'll give you some time to think and answer these questions. So the first question is actually wrong because the glass envelope contains vacuum. It doesn't have any gas, as I already described. The metal housing is designed to prevent stray light getting into the tube and to shield it from magnetic fields. This is a true statement. It shields it from external light source as well as magnetic fields. The focusing electrodes are designed to channel photons from the input screen directly towards the output screen. So at first instance, you will think that this is a right statement, but this is a false statement. The focusing electrodes does channel, but it doesn't channel photons. It channels electrons because after conversion of the X-ray photons into the electrons by the photocathode, the electrons are actually focused into the output screen by the focusing electrodes. This is a false statement. The input screen is much larger than the output screen is actually a true statement because the output screen is 1/10 the diameter of the input screen. That is why minification gain occurs. The input phosphor is one large flat crystal. So again, we discussed it. Multiple needle-like crystals form the input phosphor. One large crystal is actually seen in a gamma camera, not in a fluoroscopy. In gamma camera, we have a sodium iodide helium crystal, one large crystal. So these are the answers to the questions. Now solving the second question of my MCQs. So in an image intensifier, electrons from a photocathode are accelerated towards the output screen via a series of diodes. The statement is true or false? So it's a false statement because diodes are not present within an image intensifier. They are present within a photomultiplier tube in a gamma camera. And electrons are not accelerated by the electrodes within the image intensifier. There is a potential difference because of which the electrons are excited. The electrodes are actually focusing it from the input screen to the output screen. Secondly, approximately 1 lakh light photons are emitted from the output screen for every X-ray photon detected. That is a true statement which you have to remember. Output is usually viewed directly by a TV camera is also a true statement. The inner side of the screen is the photocathode, which emits electrons when the X-ray beam hits it. It's a true statement. The inner side of the screen is photocathode. Outside is the phosphor. Image intensifier has an anode with a positive potential of 25 volts. This is a false statement. It's 25 kilovolts. Image intensifier emits light bright enough to be seen with the naked eye. That is a true statement. The input phosphor can pick up approximately 60% of the incoming photons. Yes, 60, 70% correct. It's a true statement. So these are the answers to that question. So now coming to another question on image intensifier, brightness gain. So it's a ratio of input phosphor brightness to the output phosphor brightness. So it's a false statement. It is a ratio of output phosphor brightness to the input phosphor brightness. It is only through minification of the image. Again, a false statement. It is a product of minification gain and flux gain. Overall, approximately 50-fold brightness gain is present. This is again a false statement. Minification gain in itself is 100-fold and flux gain is again 100-fold. So it is much more than this. Increases with increasing voltage across the intensifier is true because it increases flux gain. It increases if the output phosphor size is increased. So false statement. When the output phosphor size increases, the minification gain decreases. If the minification gain decreases, the brightness gain decreases. So these are the answers to those questions. So now coming to my next question, increasing the level of difficulty as we go along. So regarding the image intensifier, the conversion factor is the ratio of luminescence of the output phosphor to the input exposure rate. True or false? So it's a true statement. Magnification gain is the increase in brightness due to geometric magnification. So this is a false statement. It is increase in brightness due to geometric minification. It is a product of minification and flux gain. The radiation exposure rate is lower for fluoroscopy than for radiography. True or false? Now it looks like a true statement that fluoroscopy has more radiation exposure. But the thing is the radiation exposure rate is asked. And rate is lower for fluoroscopy than for radiography, conventional radiography. Because we have to we have to give the exposure for a longer period of time in fluoroscopy, and hence the rate of exposure is actually lower. Though total exposure dose for radiograph is lower than for radiography, than for fluoroscopy, that is a true statement because total exposure dose in a radiograph is lower than that of fluoroscopy because small radiation dose at a smaller rate is given for a long period of time in fluoroscopy, and hence total exposure dose increases. Electron lenses work to accelerate electrons towards the anode. True or false? This is again a false statement. Electron lenses actually have a fixed positive potential which focus the electrons which are released from the photocathode towards the output screen. They are not diodes which accelerate. Diodes have increasing positive potential within the photomultiplier tube in a gamma camera, which accelerate the electrons. Here there is a potential difference that is applied across the input and the output screen, and the electrons focus them. The electrodes focus the electrons towards the output screen. So their job is not to accelerate. Okay. So these are the answers. So these were only a few initial questions from my chapter. Now we'll be discussing some key concepts on fluoroscopy itself from my chapter. So in my key concepts, I have described some basics, for example, the structure of image intensifier and the things that are required to be remembered for the questions. So magnification is achieved electronically by bringing the electron beam crossover point closer to the input screen, and the formulas for brightness gain, minification gain, and this luminescence gain I have given in my book. So these statements I have gathered from various solving various MCQs. And if at all any of such statement comes in your exam, you will directly be able to answer it without thinking. For example, input screen is 150 to 400 millimeters in diameter. Radius of the input screen is equal to the distance of the screen to the focal point of the electron beam. So these things are not given in the books, but these are some true statements. Cesium iodide crystals are perpendicular to the screen as their arrangement reduces the scatter of light. The output screen is 25 to 35 mm in diameter, that is 1/10 of the input screen, and its thickness is in micrometers. So they have asked these questions as to output screen measures 3 mm in thickness. So we know that it is in micrometers. Overall image quality is determined at the point in the image formation process where the number of photons that contribute to the image is least. An input screen is the quantum sink in the system. So these statements we have to remember. So a quantum sink is the input screen. Skin dose may be 300 times higher than the dose at the input phosphor. Spatial resolution of the fluoroscopy is limited by the output screen. Spatial resolution of the output phosphor is better than the display monitor. Input screen is maintained at a negative potential with respect to the anode with a potential difference of 25 kilovolts. So I'm stressing on this statement again and again because it has been asked multiple times. Focusing electrodes are metal rings within the tube that are held at positive voltage with respect to the photocathode. So they are positively charged, but they have a fixed positive charge, unlike diodes, which have increasing positive charge. K edge of iodine and cesium are to be remembered because they are factual questions which have been asked. That is, iodine, because of the atomic number, it is less. It is lesser than cesium, and hence the K edge is also lesser than cesium. Leakage from the X-rays from the tube housing is typically 5 microgray per hour at 1 meter distance. X-ray scatter from the patient accounts for most of the stray radiation. So these are the statements that you have to remember for all your MCQs. Sorry, true and false questions. So that when you see it, you can directly answer it as true or false. Now this is a bonus question which you can answer in your after this particular video on your comment in the comment section. Answer will be revealed to you in the comment section itself.